Hey guys, welcome back. In this video, we're going to look into contact forces, meaning the examples of circular motion where, let's say, you're rotating this water bottle and you may imagine that why would the water not fall down at a certain speed and it stays stuck to the bottom of the bottle. So, we're going to look at the contact force which is responsible for this odd behavior. So in this example, we're taking a set of springs, putting it in a box, a container, and we're going to rotate the container. Fair enough. So let's say you're putting the object at the topmost position of the circle and you're trying to rotate it. What are the forces acting on the set of springs? The springs are at the bottom of the box or container. And when it is at the topmost position over here, the springs are in contact with the box. Being in contact means the ground or the container, the bottom of the container will apply a force on it. This calculator is sitting on at the top of my hand. Now, since the two objects, my hand is not an object, but since the object is in contact with my hand, that means there is some sort of contact force. In this example, the contact force is going to be the reaction force. What is the reaction force? The weight of the calculator. So if we know that, in this case, since the spring and the container is in contact, there must be some sort of contact force. Fair enough. So if we write down the equation for the springs only, the F net or the resultant force will be given by the weight which is acting downwards, that is the weight of the springs. The weight of the springs, not the container. Springs plus the contact force. Mind you, the contact force is acting in this direction. Why? Because the set of springs are at the top of the container. In this example, logically it's at the bottom of the container, but since it's at the topmost position, it's inverted and it's at the topmost position. So let's say you're taking this calculator and it is stuck at the top of my hand. At the bottom of my hand. That means that there's a contact force on the calculator downwards. Right? So on the spring, there's going to be a reaction force which is going to be downwards. Fair enough. So if we want to figure out the F net or the sum of forces or the resultant force is going to be given by the weight of the springs and the reaction force by the container on the springs. So let's write it down. By container on the springs. Great. So now we know our equation. And if we make the reaction force, the force by container on the springs, the subject, we have made the reaction force the subject, and we can see that the reaction force is given by centripetal force minus the weight of the springs. Fair enough. If we substitute the value of the expression for Fc is equals to mv square by r, we get mv square by r minus mg. Great. Now this equation is going to help us a lot to deduce a lot of things. So if we say that I, who is rotating this water bottle, decides to increase the speed of my motion or the tangential velocity of, let's say, this container, if we increase the value of the velocity, the tangential velocity with which I'm rotating the object, I can say that the value for centripetal force is going to increase. It is going to increase though, right? Because if Fc is given by mv square by r and you increase the value for velocity, the value for Fc or centripetal force is most definitely going to increase as well. Fair enough. So we know we increase the velocity, and if we increase the velocity, Fc increases. Phenomenal. So what happens next is the normal contact force or the reaction force will also increase. Why? Because you know mg is a constant. It doesn't change. What changes? Fc. What are you changing? Fc. What are you doing to Fc? You're increasing it. Great. So if Fc increases, N1 or the normal contact force will increase. Since this is increasing and this is staying the same, the normal contact force increases. Fair enough. If we look into another example and say, I don't have much strength and I'm going to decrease the velocity and decrease the tangential velocity. What happens in that case? If I do decrease the tangential velocity, we can say if v squared decreases, the velocity decreases, so v squared decreases, we can say Fc or centripetal force decreases as well. Great. So what does that give us? We're saying Fc decreases. If v decreases, centripetal force also decreases. In that case, since this is decreasing and this is a constant, this is not changing at all, we can say N1 or the contact force is also decreasing. Now, the question is, how far along or how much will the reaction force or the contact force decrease? So for that, we know that the normal contact force will decrease up until it is 0. Meaning the value up till which the water, or let's say the springs, are no longer in contact with the bottom of the container, that means the normal reaction force is 0. There is no contact between the springs and the container. So, if we want to find out the least value for velocity for which I need to rotate the container, I need to apply the contact force as 0 because I want to figure out the minimum velocity. Now you may ask, if the contact force is 0, then what's the point of figuring out the velocity? Because if the contact force is 0, that means whatever velocity I find out, the water is not going to be in contact with the bottom of the bottle. However, this is a trick part. We are saying at the topmost position, only at the topmost position, instantaneously, the value of contact force is going to be 0. Mind you, it's going to happen instantaneously. In this example, you can see the water is no longer in contact, and this is not instantaneous. What would be instantaneous? If for only a very, very, very small moment, the water would lose contact with the bottom of the bottle. Meaning, if for barely a short period of time, momentarily, it loses contact, that would be instantaneous. Therefore, if I apply the same logic as before in the previous videos, I've already mentioned this. If the tension momentarily or instantaneously is 0, no problem. It will have inertia and will move rightwards and will regain tension. In this case, since momentarily we are taking reaction force as 0, after that specific instant when the water bottle moves rightwards, in that case, it will start or regain the contact force. The bottom of the bottle will again be in contact with the water after that instant at the topmost position. So, there's no problem if we take N1, the value or the magnitude for contact force to be 0. Since after that specific moment, the contact force may be regained. Therefore, to find out the velocity, the minimum velocity, it is okay for us to consider or assume contact force as 0. Fair enough. So, the velocity minimum required to keep the spring in circular path is going to be given by when the normal contact force is 0. So, if we plug in 0 in the equation, in this equation, we are getting Fc is equals to mg, and back to the previous equation, we have velocity is equals to root rg. So, the same as before, if you apply the contact force is 0, you will get the minimum velocity. So, in both examples, the formula is V is equals to root rg. Fair enough. Now, another example of the same set of springs, but in the lowest position now. What's going to be the case in this example? Let's write down the forces on the spring. F net, meaning the net force acting on the spring, is going to be given by the contact force, which in this case, surprisingly, is acting upwards. Why? Because the spring is in contact like this and at the vertically below position, or it's vertically down, meaning mg is acting in this direction. So to counteract that force, Newton's third law, the reaction force is upwards. Agreed? Fair enough. So since the reaction force is acting upwards towards the center, we have taken it to be positive. And mg is acting away from the center, it is negative. Fair enough. So the net force is given by N2, the normal contact force between the spring and the container, meaning the force that the container applies on the spring is N2. So the F net is given by N2 minus mg. Fair enough. So we can make the normal contact force the subject and say that the reaction force is the sum of centripetal force and the weight. So what is the normal force doing? This N2 is providing both the centripetal force and also counteracting the weight. So it's nullifying the value of weight and also giving you a resultant centripetal force. So it's doing both of them. Fair enough. So if I substitute the value for Fc, we have N2 is equals to, or reaction force is equals to mv square by r plus mg. Now from this equation, again, similar to the cases where tension is figured out, we know if the object is in the lowest position, the value for the reaction force is going to be greater than this reaction force. Why? Because it is at the topmost position. It is at the topmost position, in which case we get Fc minus mg. So the normal reaction force in this case is less compared to this. So we can say at the topmost position, contact force is minimum, and at the lowest position, the contact force is maximum. So we can say N2 is greater than N1. This is the first example, and this is oh my god. This is this example. Fair enough. So next we can look into a few examples.